हेलो। हेलो।
हेलो.
हाँ, येतोय का आवाज माझा? Okay, you can see the screen also, no? There,
Yes, yes,
my
ma'am.
PPTs, all PPTs.
हाँ.
Okay, just check this one.
Yes, ma'am.
Hmm?
Perfect. Yes.
Okay, no?
Okay, okay.
Okay, my voice is there. Everything
Yes,
is
yes,
fine.
ma'am.
Okay.
Yes, ma'am.
So tell me when to start. I will start at that time. Okay. हॅलो. हां, बोला. हां, पण लवकर मला पण करायचंय त्याच्यामुळं. हां, पण त्यातून काही मला ऐकू येत नाहीये कुणी काही बोललेलं. हां, आत्ता कोणी काही बोलत नाहीये ना? सुरू कधी करणार आहे तुम्ही एक्झॅक्टली? ओके, ओके. फाईन. हं.
Good afternoon, all. Now, for this session, academic session of the day, it will be delivered by an eminent academician and the researcher. It is my privilege to introduce Dr. Renuka S. Gaun, Associate Professor in the Department of Computer Engineering at PCET, Nutan Maharashtra Institute of Engineering and Technology, Talegaon Dabade, Pune. She holds a PhD in Computer Engineering from Savitribai Phule, Pune University, am MTech from Bharati Vidyapeeth Deemed University and a BE from Shivaji University, Kolhapur, with other 21 years with over 21 years of teaching experience. She has served in various academic leadership positions, including head of the department AIDS. Her expertise spans cloud computing, artificial intelligence, image processing, operating system, Java, Linux, system programming, satellite image processing, QGIS, and Python. She has published research papers in Scopus Index journals, IEEE conferences, and Springer book chapters. Now I request, ma'am, please start your session. Welcome, ma'am. Thank you.
Thank you, ma'am. Okay. It's my privilege to present this faculty orientation program for third year engineering, the presentation on cloud computing unit 5. So we'll directly start with our presentation. So we are having unit 5. Unit 5 is basically focusing on a modern cloud environment and emerging technologies. So you have to take the 9 hours for this particular unit. It should contain the future trends in cloud computing. So many trends are there that I will show you one by one in the slides. Then the comparison in between distributed cloud computing, edge computing. Then some different clouds like Docker, Kubernetes, pod management, green cloud, sustainability, then energy efficient data center design, and carbon footprint tracking. So we will start our presentation. So first thing is there future trends in cloud computing. So cloud computing is already started around in 2006. Still, we need the future trends. Why? The answer may be like this: more users will be there, more data is there, faster applications are there, then AI, artificial intelligence is there, security is there, internet of technology is there. So technology is changing rapidly, so cloud computing must also evolve. These new developments are also called the future trends in the cloud computing. So imagine 20 years ago, Gmail, Facebook, YouTube were there. That were enough for us. But now we are using ChatGPT, self-driving cars, smart cities, IoT, 8K video streaming, digital twins. Can the old cloud can handle all these things? Yes, it can handle, but not efficiently. Therefore, cloud evolves continuously. Today we are looking at the evolution of cloud computing. It's easy to think of the cloud as a single technology, but it is actually a continuous journey. We have moved from managing physical boxes in a black room to orchestrating global intelligent networks. Let's walk through the 6 major areas of this evolution. So you can see this figure. This is focusing on the evolution of cloud computing. So cloud is not a fixed technology. Every few years, new technologies are added to solve the new problems. So we will focus on this major areas. So we can see from this one, left to right, we're having traditional computing, virtualization, cloud computing, serverless, edge AI, and intelligent cloud. So in the traditional computing, we can see here, we can start on the far left with the traditional computing. This represents the classic on-premise data center. If a company needed to launch any application, they had to buy physical servers, stack them in a room, and maintain them manually. It was high maintenance, expensive, and incredibly difficult to scale quickly. Then comes virtualization. That was the first massive shift with the virtualization. Instead of running just one operating system per physical server, software allowed us to split one physical machine into multiple virtual machines. This drastically increased efficiency, cut hardware cost, and laid the actual architectural groundwork for what we know as a cloud. Once virtualization was mastered, it moved to global scale, bringing us to cloud computing. This introduced the concept of, we know that IaaS, PaaS, SS. Instead of owning the hardware, business could now rent processing power and storage on demand with a pay-as-you-go model. It leveled the playing field, allowing startups to access the same global infrastructure as massive enterprises. Then comes serverless. In the serverless, as the cloud matured, we wanted to stop managing infrastructure altogether. That brought us to serverless computing. Despite the name, servers still exist, but developers don't have to worry about them. You simply write code like a microservices or scalable functions, and the cloud provider automatically triggers, scales, and manages the underlying resources only when the code runs. Then Edge AI. It's a decentralization, but sending every single piece of data back to the centralized cloud data center creates the latency that brings us to Edge AI. Instead of processing data thousands of miles away, we push the computational power and AI models directly to the edge, meaning onto local devices like smartphones, IoT sensors, local gateways. This allows for near instantaneous decision making and low latency. Then comes intelligent cloud. Finally, we arrive at the intelligent cloud. This is where everything converges. The cloud is no longer just a place to store data or run code. It is interconnected system embedded with AI and machine learning. The cloud itself handles predictive analysis, automates massive decision making pipelines, and continuously optimizes the operation autonomously. So these six trends are there, and the new trends will start with this one. First trend is like a AI cloud. So we can see this slide here. This diagram illustrates the concept of AI cloud, where the artificial intelligence services are delivered through cloud computing. Instead of installing expensive AI software and hardware locally, user can access AI capabilities over the internet on a pay-as-you-use basis. Let us understand the working of AI cloud from left to right. First, we have to see we have the input here, different types of data such as structured data, images, text, voice, and sensor or IoT data are collected from the user or devices. This data is sent to the cloud platform for processing. At the center, AI cloud platform. It contains machine learning models, data analytical tools, AI services, and APIs. The cloud provides powerful computing resources that processes image amounts that processes large image or large amounts of data efficiently. This working process is simple. The data is first uploaded to the cloud, where AI model analyzes and learns from it. After processing, the cloud returns intelligent results to the user or application. On the right side, we can see the output generated by AI cloud. This includes predictions, automation, recommendations, insights, and smart decision making, helping organizations make better business decisions. At the bottom of the diagram, it highlights the benefits of the AI cloud. It eliminates the need for expensive hardware, offers scalability, follows a pay as you use pricing models, supports faster innovation, and makes AI solutions easier to integrate into applications. Some popular AI cloud platforms are Google AI, Microsoft Azure AI, and AWS AI services. Finally, AI cloud is widely used in chatbots and virtual assistants like ChatGPT, image recognition systems such as Google Photos, fraud detection in banking, predictive maintenance in industries, and medical diagnosis in healthcare. In summary, AI Cloud combines the power of artificial intelligence with the scalability of cloud computing, enables organizations to build intelligent applications without investing in costly infrastructure. I hope everyone understands this AI cloud. So we'll move to the next slide, that is containers. This diagram explains the concept of containers, which are a lightweight virtualization technology used to package an application along with all dependencies, ensuring that it runs consistently in any environment. Let us understand the diagram section by section. On the left, we are having what is a container. A container includes the application, required libraries, dependencies, and configuration files in a single package. This eliminates the common problem of it works on any machine but not on yours. In the center, the container architecture is shown. Multiple containers can run on the same host operating system using a container engine, such as a Docker. Each contains each container has its own application and dependencies, but shares the host operating system kernel, making the container lightweight and efficient. On the right, the diagram compares container and virtual machines. Virtual machine requires a special guest operating system. One second, excuse me. So on the right side, diagram compares the containers and virtual machines. Virtual machines requires a separate guest operating system for each application, making them large and slower. Containers, however, share the host operating system, resulting in faster startups, lower memory usage, and better resource utilization. At the bottom, the working process is illustrated. The developer writes the application. A Docker file is used to build a Docker image. A Docker image contains an application and all required dependencies. Finally, the image is executed as one or more Docker containers, which can run consistently on any machine. The key benefits include lightweight execution, portability, consistency across environment, and easy scalability. Containers are widely used for microservices deployment, CI/CD pipelines, cloud native applications, development environment, and AI or big data workloads. A well-known real-world example is Netflix, which uses thousands of Dockers containing containers to deploy microservices. This enables high availability, automatic scaling during peak traffic, and faster delivery of new feature to millions of users worldwide. In summary, containers package application and their dependencies into a lightweight portable unit, making software deployment faster, more efficient, and consistent across different computing environments. So next trend is Kubernetes. This diagram contains Kubernetes, commonly called K8s, which is an open source platform used to automate the deployment, scaling, and management of containerized application. While Docker helps us create and run containers, Kubernetes helps us manage thousands of containers efficiently. Let's understand the diagram section by section. On the left, Kubernetes provides features such as automatic deployment, application scaling, self-healing, rolling updates, service discovery, load balancing, and efficient resource utilization. This features makes it ideal for managing large cloud applications. In the center, we have the Kubernetes architecture. It consists of control panel, master node, and multiple worker nodes. The control plan manages the entire cluster through components like an API server, scheduler, controller manager, and etcd, which stores the cluster information. The worker nodes are responsible for running the application inside pods. Each worker node contains a kubelet, which communicate with the master node and kubeproxy, which manages network communication between pods. At the bottom, the working process is shown. The developer creates a YML manifest. What is this YML? It is a text file that describes the configuration of Kubernetes resources such as pods, deployment, and services describing the application. The configuration is applied to Kubernetes cluster using kubectl command. The scheduler selects the most suitable worker node. The kubelet starts required pods on the node. Kubernetes continuously monitor the application and automatically restarts failed pods or creates additional pods when traffic increases. The key benefits include automation, scalability, high availability, portability, and efficient utilization of computing resources. Kubernetes is widely used for microservices deployment, auto scaling application, high availability system, and cloud native application. A real world example is Netflix, Spotify, Uber, Airbnb, which uses Kubernetes to manage thousands of containers and serve millions of users. During peak hours, Kubernetes automatically creates additional pods to handle increased traffic and removes them when demand increases. So, Kubernetes is a powerful container orchestration platform that automates deployment, scaling, load balancing, and self filling, making modern cloud applications reliable, scalable, and highly available. So, we'll see here now what is this pod? Pod management actually. A pod is the smallest deployable unit in Kubernetes that contain one or more containers sharing storage and networks. See this figure now. When an application is deployed, Kubernetes creates pods based on the deployment configuration. The Kubernetes scheduler automatically assigns pod to the worker nodes based on the available resources. The pod management provides automatic deployment, scaling, self-filling, and efficient resource utilization. Then comes edge computing. This diagram explains edge computing, a computing paradigm in which data is processed close to where it is generated. Instead of sending all the data to the centralized cloud, this enables faster responses time, reduced latency, and real-time decision making. Let's understand the diagram from left to right. On the left, the diagram highlights why edge computing is important. Since the data is processed near the source, it provides low latency, reduces the amount of data transferred to the cloud, improves reliability even when internet connectivity is limited, enhances data privacy and security, and lowers bandwidth and operational cost. In the center, the working of edge computing is shown. The data is generated by sources such as cameras, IoT devices, sensors, and vehicles. Instead of sending all the data directly to the cloud, it is first reaches the edge layer, which consists of edge server or gateway. Here, the data is processed, filtered, and analyzed locally. Only important or summarized information is then forwarded to the central cloud for long term storage, advanced analytics, and AI model training actually. On the right, the diagram compares edge computing with the cloud computing. Edge computing performs processing near the devices, offer low latency, supports real-time applications, and reduces internet dependency. Cloud computing, on the other hand, provides centralized processing, large-scale storage, backup, and advanced analytics, but generally has higher latency. Edge computing brings computation closer to user and devices, enabling faster processing, lower latency, then reduced bandwidth usage and efficient support for real-time applications. Next comes mobile cloud computing. The diagram explains mobile cloud computing, which combines mobile computing and cloud computing. Instead of performing all processing and storage on the mobile device, resource-intensive tasks are offloaded to cloud server. This enables mobile devices to run powerful applications with better performance. Let us understand the diagram from left to right. On the left, the diagram defines mobile cloud computing devices such as smartphones, tablets, wearables, and laptops access cloud resources over the internet. The cloud performs storage, processing, and computation, and the results are sent back to the mobile device. This helps overcome the limitations of mobile devices such as limited storage, battery life, and processing power. In the center, the working of mobile cloud computing is illustrated. A mobile device sends a request through the internet using Wi-Fi, 4G, or 5G to cloud servers. The cloud servers provide services such as storage, computation, application, and security. After processing the request, the cloud sends the response back to the mobile device. The architectural overview shows that the mobile devices act as a thin client, while the cloud data center performs the heavy computation and stores the data. On the right, the key benefit is highlighted. Mobile cloud computing overcomes hardware limitations, reduces the need for expensive devices, improves the battery life by offloading computations to the cloud, provides scalability, and ensures the applications and data remain up to date. Some popular platforms supports mobile cloud computing. They are like Google Firebase, Microsoft Azure Mobile Services, AWS Mobile Services, IBM Mobile First, and Apple iCloud. The application include cloud storage using Google Drive or OneDrive. AI-powered voice assistants like Google Assistant and Siri, video streaming through YouTube and Netflix, mobile gaming, mobile banking applications. A real-world example is Google Photos. So mobile computing extends cloud capabilities to mobile devices by providing powerful computing, storage, and applications over the internet. It enables users to access services anytime, anywhere, while reducing the limitations of mobile devices. Next is Comet Cloud. So see the diagram. This diagram explains the Comet Cloud, an advanced cloud computing model that extends cloud and edge computing by using dynamic, decentralized, and mobile resources. Instead of relying only on fixed cloud data centers, Comet Clouds can utilize nearby devices such as smartphones, vehicles, drones, and edge nodes to provide computing resources. Let's understand the diagram section by section. On the left, the diagram explains why Comet Cloud is needed. It offers ultra-low latency by processing data close to users, adapts to changing network conditions, provides decentralized resilience, enhances privacy by keeping sensitive data local, and optimizes resources by using the ideal computing power of nearby devices. In the center, the working of Comet Cloud is illustrated. Devices such as self-driving cars, drones, smartphones, and public bases act as a Comet nodes. These nearby devices form a temporary network and share their computing resources with each other. They perform local processing and communicate with the central cloud, which is responsible for large scale storage, AI/ML processing, backup, and global resource management. In this way, computation is shared between local node and the cloud. On the right, the comparison shows that Comet Cloud differs from traditional cloud and edge computing. Unlike centralized cloud computing or fixed edge servers, Comet Cloud uses dynamic and mobile nodes, provides ultra low latency, and is well suited for ad hoc and decentralized application. Some applications include vehicle to vehicle communication, smart cities, drone swarm, peer to peer resource sharing, multiplayer virtual reality, and mobile retail services. A real world example is disaster management. During floods or earthquakes, communication infrastructure may fail. Rescue teams, smartphones, drones, and emergency vehicles automatically form a temporary Comet Cloud network to share information, process local data, and coordinate rescue operations without depending entirely on the internet or the centralized cloud. So Comet Cloud combines the strength of cloud computing and edge computing by using nearby mobile devices such as computing resources. It provides low latency, efficient resource sharing, high resilience, and supports real-time applications in dynamic environments. Next is Multimedia Cloud. So Multimedia Cloud refers to the delivery, storage, processing, and management of multimedia contents like audio, video, images, animations, and streaming media using cloud computing technologies. It provides scalability resources for multimedia applications while ensuring high availability, reliability, and quality of service. So this slides explains the working of Multimedia Cloud, which enables the storage, processing, management, and delivery of multimedia contents such as video, audio, image, live streaming, and text over the internet on demand. Let's understand the process step by step. Step 1, content sources. On the left side, different types of multimedia contents are created, including videos, audio files, images, live streams, and metadata. These contents are uploaded to the multimedia cloud. Step 2, Multimedia Cloud Platform. This is the core of the system. It performs 5 important functions. First is ingestion. The uploaded content is collected and imported to the cloud. Storage. The content is stored in scalable cloud storage so that it can handle large volumes of data. Processing. The cloud performs operations such as transcoding, compression, and final conversion, making the content compatible with different devices and reducing file size. Management. Metadata is added, content is organized, user access rights are managed, and files are cataloged. Delivery services. The platform prepares the content for streaming using load balancing, quality of service, and streaming services. All these services run on the cloud infrastructure, which includes virtualization, server, storage, and networking. Step 3 is content delivery network, that is called as a CDN. The processed content is then distributed through CDN. Edge servers located closer to users reduce latency and ensure fast and smooth streaming. Step 4 are end users. Finally, users can access the multimedia content on various devices such as smart TVs, mobile, laptops, tablets, and desktops anytime and from anywhere. Step 5, management and analytics. The cloud continuously monitors system performance, performs analytics, ensures security, manages configuration, and generates report to improve overall service quality. The major advantages of multimedia cloud are global accessibility, high scalability, cost efficiency, high availability, reliability, and security, better quality of service. A multimedia cloud efficiently stores, processes, manages, and delivers multimedia content over the internet, providing users with a fast, secure, and high quality access across multimedia devices. Next is the IPTV. So, what is this IPTV? This slide explains the working of IPTV, which stands for Internet Protocol Television. Unlike traditional cable or satellite TV, IPTV delivers television channels and video services through an IP-based internet network. It provides live TV, video on demand, and time-shifted TV. Let us understand the working step by step. First is content sources. On the left, different types of contents are collected, such as live TV channels, video on demand, like movies and shows, local event recordings, and audio content. These are the original sources of IPTV content. Second is the head-end system. The content is sent to the head-end system, which is the processing center of IPTV. Here, the content is received. It is encoded and transcoded into the suitable digital formats. It is compressed to reduce bandwidth. Multiple channels are multiplexed together. The content is encrypted for security. Finally, it is stored on a servers for streaming. Next is the IP network. The processed content is transmitted through the internet or ISP network. A content delivery network with edge servers distributes the content closer to the users, reducing latency and improving streaming quality. User premises at the user's home, the broadband internet connects to the home router. A set-top box receives the IPTV content, displays it on the TV through an HDMI connection. The same content can also be accessed on laptops, tablets, and smartphones. IPTV services. IPTV provides three major services: live TV for watching channels in real time, video on demand to watch movies or shows anytime, time shifted TV to watch previously aired programs whenever convenient. The major advantages of IPTV are high quality HD, 4K streaming, on demand content, interactive services, support for multiple devices, cost effectiveness, better user experience. To include IPTV collects multimedia content, processes it at the head end, delivers it through IP networks and CDNs, and stream it to users on different devices. It offers a flexible, high quality, and interactive television experiences compared to the traditional broadcasting. Next is energy aware cloud computing. This diagram shows the concept of energy aware cloud computing. The objective is to reduce energy consumption while maintaining cloud performance. User request first reach to the cloud infrastructure. The cloud continuously monitors the utilization of servers, virtual machines, storage, and networking resources. If some servers are underutilized, workloads are consolidated onto fewer servers using virtualization. The idle servers are either switched off or placed into lower power mode. The cloud also applies techniques such as dynamic voltage and frequency scaling, efficient workload scheduling, resource optimization, and load balancing. Renewable energy sources like solar and wind power may also be integrated to reduce dependencies on conventional electricity. Finally, monitoring tools continuously measures power usage and optimize resource allocation. These techniques reduce electricity cost, minimize carbon emission, and improve the overall sustainability of cloud infrastructure. Next is the comparison in between distributed cloud computing and edge computing. This figure compares distributed cloud computing and edge computing. In distributed cloud computing, cloud services are deployed across multiple geographical regions while being centrally managed by the cloud provider. This improves reliability, availability, and disaster recovery. In contrast, edge computing processes data much closer to where it generated, such as IoT devices, sensors, or local edge servers. Distributed cloud reduces regional latency by replacing cloud resources closer to the user, whereas edge computing minimizes the latency even further by processing data locally without sending everything to a central cloud. Distributed clouds is suitable for global applications like cloud storage and enterprise services, while edge computing is ideal for real-time applications such as autonomous vehicles, smart factories, and healthcare monitoring. Together, both approaches improve application performance and reduce network congestion. Next comes green cloud computing. This diagram demonstrates green cloud computing, which focuses on minimizing the environmental impact of cloud infrastructure. User requests are processed by cloud servers while continuously monitoring power consumption. The cloud uses virtualization to consolidate workloads, reducing the number of active servers. Renewable energy sources such as solar and wind power supply part of the electricity required by the data centers. efficient cooling system, intelligent resource scheduling, and energy-aware hardware further reduces the energy consumption. Monitoring system tracks energy usage and carbon emissions in real time. The result is lower electricity costs, reduced greenhouse gas emissions, improved sustainability, and environmentally friendly cloud services. Next is sustainable cloud architecture. This figure presents sustainable cloud architecture. The architecture begins with user accessing cloud services through the internet. Requests are handled by cloud servers that use virtualization and containerization to maximize hardware utilization. The infrastructure integrates renewable energy sources, energy efficient servers, intelligent cooling systems, and automated resource management. AI based monitoring continuously analyzes workload patterns and dynamically allocates resources only where needed. Unused resources are released automatically, reducing unnecessary power consumptions. This sustainable design minimizes operation costs, lowers carbon emission, improves system reliability, and supports environmentally responsible cloud computing. Next comes energy efficient data center designs. This diagram explains the design of an energy efficient data center. The objective is to minimize energy consumptions while maintaining reliable cloud services. Power enters the data center from the electrical grid or renewable services and passes through efficient power distribution systems such as UPS and PDUs. Servers, storage devices, and networking equipments are arranged using hot aisle and cold aisle layouts to improve airflow. Advanced cooling technologies remove excess heat efficiency, reduces electricity usage. Monitoring system continuously measures temperature, power consumption, and equipment performance. The combination of efficient hardware, optimized cooling, renewable energy, and intelligent monitoring reduces operational cost, improves reliability, and supports sustainable cloud computing. The last one is carbon footprint tracking. This figure illustrates the process of carbon footprint tracking in the cloud computing. The process begins by collecting data from different sources, including data centers, cloud services, electricity consumptions, transportation, and equipment usage. The collected data is analyzed using standard emission factors to calculate carbon dioxide equivalent carbon dioxide CO2 emissions. The system continuously monitors emissions through dashboards and reports, allowing organizations to identify major sources of carbon emissions. Based on this analysis, organizations implement strategies such as energy optimization, renewable energy adoption, efficient resource utilization, and workload consolidation. Regular reporting helps organizations meet sustainability goals and environmental regulations. Carbon footprint tracking enables organizations to measure, monitor, manage, and reduce gas emissions, supporting the development of greener and more sustainable cloud infrastructures. This is the last point from the syllabus. So you can refer this references which I have given in the slide. The Booyah book you can use Mastering Cloud Computing Foundation and Application Programming, Distributed and Cloud Computing from Parallel Processing to the Internet of Things, Cloud Computing Concept, Technology and Architecture. Some links are also given there so that you can refer the contents from the slide. So I hope everyone understood what to take in the Unit 5. If you are having any doubts, you can come to me.
Any questions, anyone? Okay. Thank you so much, ma'am, for the detailed and engaging brief on the Unit 5. Your breakdown of the modern cloud environment and emergent technologies in cloud computing provide us with great clarity on the syllabus. Thank you once again, ma'am, for your support. I request Dr. Khushbu, ma'am, to deliver the vote of thanks.
Good afternoon, everyone. As we come to the conclusion of inaugural session of Faculty Orientation Program on Cloud Computing, it is my privilege to propose the vote of thanks. On behalf of Department of Computer Engineering, Trinity Academy of Engineering, I express my heartfelt gratitude to our Honorable Founder President Shri Kalyan Jadhav Sir for his constant encouragement, visionary leadership, and unwavering support towards academic excellence. I sincerely thank our esteemed Dr. Nilesh Uke sir, BOS member and chairperson Savitribai Phule Pune University for gracing this occasion and guiding us with his valuable presence. My heartfelt gratitude to our distinguished resource persons, Mr. Sagar Umarkar sir, for sharing his expertise on cloud platform and applications. Uh, I, I express my gratitude to the resource person, Dr. Madhuri Shinde ma'am, Assistant Professor, MET Institute of Engineering, Nashik, for her insightful session on Introduction to Cloud Computing and Virtualization. Dr. Renuka ma'am, Associate Professor, PCCOEs, Nutan Maharashtra Institute of Engineering and Technology, Tadegaon, for her enriching session on modern cloud environment and emerging technology. I extend my sincere thanks to our Executive Director, General Major Samir Kalla sir, Technical Director Dr. Ajay Fulambarkar sir, Dean Student Welfare Dr. Hemant Deshmukh sir, and respected Principal sir Dr. R.J. Patil for continuous motivation and support. A special note of thanks to our Head of Department, Professor Rambhav Labdive sir, for his guidance, leadership, and success fully organizing this faculty orientation program. I also thank to all respected head of departments, faculty members, participants from various institutes, the organizing committee, volunteers, technical support team, every individual who contributed directly or indirectly to make this program a success. Your presence, support, and active participation have made this event truly meaningful. Once again, thank you all. We wish you a wonderful learning experience throughout the faculty orientation program. Thank you and have a nice day.
Thank you.
This is a news for participants. We will share tomorrow's hands-on session link and one of the left one session to in the WhatsApp group. Please keep checking the group. Thank you.